All right, let's get right into it. I'm Jacob White, and this is my lecture overview. So I decided to attend the lecture, Einstein's Cosmos and the Quantum, Origin of Space, Time, and Large-Scale Structure of the Universe. In this lecture, Dr. Ashtekar details the history of modern physics from Einstein's theory of general relativity to modern loop quantum gravity. The creation and early years of the universe are explored, along with new possibilities that serve to replace old models based on classical and outdated physics. Almost all physics discussed by Dr. Ashtekar was extremely new to me. However, he made these new concepts easy to understand and grasp. I found the lecture to be very interesting, as the fundamental physics of the universe and the formation of the universe are two topics that, if understood correctly and accurately, could explain and predict everything in our universe. And obviously, this would be amazing for the development of human technology. Uh, so, Dr. Ashtekar begins his lecture by discussing Einstein's theory of general relativity. Before Einstein, classical physics developed by Newton was used to explain the interactions in the universe. While Newton's equations were very accurate, there were measured phenomena in the universe that did not adhere to these equations. Einstein began his work by developing his theory of special relativity, in which the speed of light was postulated as a constant value that was the limit of speed in our universe. General relativity focused on the relationship between gravity and spacetime. Einstein postulated that spacetime was based on a fundamental geometry that could be curved and warped under the influence of mass, which was responsible for gravity as we know it. This new theory led to the Einstein field equations, which could be used to more accurately predict the effects of gravity and predict how the universe came to be. So Einstein's field equations were used to create a model of the universe called the Big Bang. The Big Bang theory is a cosmological model of the universe that describes the origin of the universe 13.8 billion years ago from a point of extremely high density and temperature that expanded to what we see today. This model is able to predict and explain many phenomena such as cosmic microwave background, which is faint radiation that fills up all space and is a remnant of the Big Bang. Using Einstein's equations, the large-scale structure of the universe observed today can be predicted extremely accurately from the cosmic microwave background. However, while Einstein's equations can be used to model how the world structure came from the cosmic microwave background, the interactions that led to the cosmic background radiation cannot be modeled using these equations, leaving a large gap unexplainable by general relativity. So here's a diagram of the Big Bang. As you can see in the beginning, there's inflation and the cosmic background radiation, and then the accelerated expansion of the universe. So quantum gravity. General relativity has long been thought as the best and most accurate depiction of gravity, as it explains and predicts most interactions in our universe. However, there are some interactions that can't be explained or predicted by general relativity, such as what happens at the center of a black hole and how the small fluctuations in the cosmic background radiation came to be. To answer these questions, a new model of gravity must be created that is able to predict how gravity interactions occur at a very small quantum level. This has led to the creation of many new theories that seek to bring gravity to the quantum realm, such as loop quantum gravity, as Dr. Ashtekar explains. Loop quantum gravity is based on creating a quantum description of Einstein's spacetime geometry using the Planck length at the smallest distance measurable. LQG is able to predict the formation of the cosmic microwave background based on small fluctuations in the quantum vacuum of space. And even more interestingly, in this new theory, a big bounce is predicted, which involves a big bang followed by a big crunch, in which the universe initially expands and then contracts in a sort of cyclical manner. This is contrary to inflation theory, which has been widely accepted in the scientific community. So after the lecture concluded, I decided to do my own independent research, and I found an important area of study related to the lecture that piqued my interest. This was particle physics. Particle physics is a branch of physics that studies the fundamental particles that make up all matter and energy we observe in the universe. The standard model of particle physics categorizes the elementary particles into three categories: the quarks, leptons, and bosons. These particles are described as excitations in the quantum field, and their fundamental properties, such as spin and mass, explain how they interact with each other. Three of the four fundamental forces of the universe, being the electromagnetic force, weak force, and strong force, can be explained through interactions of these particles, leaving us with an almost complete picture of the most basic interactions of the universe. However, gravity is yet to be explained under this standard model, as the proposed particle dictating the interactions of the gravitational field, the graviton, has yet to be observed in scientific experiments. And here's a diagram of the standard model. And that concludes my overview.